I am here.
Oh, thank the Lord. I was worried.
Back to Star Wars.
By the way, Allie's here with me.
Oh, okay, cool.
Mhm.
Thank you for doing that this morning. That was very good. Well done. Where did you get the script from?
Miss McCullis.
Ah,
Yeah, we had started like working it out before we got kicked to e-learning, but we didn't get very far. Yeah, so she finished it.
no, you guys did good.
Thanks.
Guess Ben and Jack are no shows today.
Jack's here.
I'm in the Zoom meeting.
Oh, Jack's here. Ben. Didn't see that. All right, we'll get
Yeah,
started.
he didn't answer any of my texts today.
Any questions on the homework? All right, let's go over it. Here we go. Number one, you better not have missed number one. 1/5. Number 2 is 5. Number 3 is a over 2. Number 4 is 3. Number 5 is 1/3. Did anybody put 3 as the answer for number 5? Occasionally, I'll have students will say, oh, the x's cancel, I'm left with 3. Well, 3 was in the denominator, so it's 1/3. Number 6 is c over 2b. Number 7 is negative 4y squared. Number 8 is negative 3r squared over 2. Number 9 is ab over 2c. Number 10 is, where's the answer for number 10? Oh, there it is, a plus 2. Number 11 is 3x minus 2y. Number 12 is 3a minus 2. Number 13 is 1/3. Number 14 is c minus d over c plus d. Number 15 is t plus 1. Number 16 is 5 over a minus b. Number 17 is b plus 5 over b minus 7. Number 18 is a plus 4 over a minus 4. And number 19 is 3 times the quantity x minus 4 over 3x minus 4. And that was it. Questions? Okay. All right, last class before the break. Here is your homework.
So what's this chapter about?
Oh, this I will absolutely say for many students is the hardest chapter of the book. It's on similarities. So it's going to be, basically it's going to be triangles, although we'll do a couple quadrilaterals. It's going to be triangles that are not congruent, but triangles that are similar. However, it
like
starts
with
off,
AAA and like AA.
yeah, we're going to get AAA and then a couple other ones as well too.
We just get
Right.
also like wouldn't it also be the same if you just have two angles that are congruent to two angles of another triangle?
And that's called the third angle theorem. All right, it's one of the first ones we'll do. We won't do it this section though. All right. Well, actually, we've already had the third angle theorem, but yeah. So all you got to do is show us 2 is congruent to 2, and then the third one you get automatically. All right. Ratios and proportions. Well, we did ratios and proportions many times in pre-algebra, 7th grade, 6th grade. We also did a little bit of ratios and proportions in algebra 1. It turns out you can also do it in geometry. All right, so generally speaking, get it, right? Generally speaking, it is a challenging chapter, but today is pretty simple. All right, you do have to pay attention. The very last thing we do is the one, basically the one new thing. Here we go. So we're going to be talking about ratios today, and ratios, remember, are a comparison of two numbers using division. Well, that sounds awfully lot like a fraction, and that's what a fraction is. A fraction is a ratio. We usually express ratios in simplest form. Now, we always express fractions in simplest form. We usually also do the same thing to ratios. So if I did the ratio of 8 to 12 in fraction form, it would look like this. Now, you can certainly simplify that fraction in 2/3, but you lose something. If there was, I don't know, something attached to that 8 and 12, for instance, if there were 8 boys in the class and 12 girls, if you reduce that to 2 to 3, you lose the fact that you had originally 8 girls and 12 boys, or whatever I said before. So it's not that you shouldn't reduce a ratio, it's just that if you do reduce a ratio, you lose something of the original context. What you don't lose, however, is the fact that for every 2 of this, you get 3 of this. So that part remains true, but like I said, if you reduce 8 over 12 to 2/3, then you don't even know how many you started with. All right, and also remember we have this third way of writing ratios called colon form. This is called written form, where you use the TO. This is called fraction form, and this is called colon form. And we saw that in pre-algebra. All right, how do you do ratios in geometry? Well, it's not any more complicated. They're going to give you a shape of some sort and give you some information and ask you to set up a ratio. So if we were to do the ratio of OI to ZD, well, OI is 14 and ZD is 6B, so it's not any more complicated than what you would think. If I do OI to ZD, remember in fraction form, it will go exactly the way it appears. This will be your numerator, this will be your denominator. So it will be 14 over 6B. We certainly could, if we choose to reduce this, to 7 over 3B. Homework, they assume that you would like to reduce the fractions, okay? They could get a little bit tricky, you know, they could say the ratio of the smallest angle to the largest or largest to smaller. And just be careful because notice we only have 3 of the angles here. How big is angle O?
Angle O would be
Purple.
No.
110, 230.
Let's
So
see.
it would be
N minus 2 times 180 would give us all the angles. It's got 4 sides. 2 times 180 at 360. So we know all the angles added up would be 300.
so it's 130 degrees. Oh,
130. That's 130 plus 120 is 250. So,
oh, never mind. So then it's 110.
So it's 110. So just be careful, right? If it said smallest to largest, right, and there's one is missing or 2 is missing, make sure you figure out what they are before you make your conclusion. But in this case, if I do smallest, well, that's pretty easy. 60 is the smallest and 120 is the largest. So that's pretty easy to do. All right.
Couldn't we also have just figured out that because it was supplementary to 70? That would have been much easier.
Well, if we knew it was a trapezoid, and if we knew it was further, if we knew it was, remember, that's only if ZO is parallel to DI. Nowhere in here did it say that. So, but if it was, yeah, we could have done that.
Well, can't we say that they are parallel now because both of those are supplementary?
Yes, we can. Right. Absolutely, we absolutely could. Now that you bring that up, we actually could have said that because this was 60 and that's 120. So yeah, that would have, we could have made that leap of faith there as well too. All right. Okay. All right. Well, that isn't too bad. Now they are going to raise the specter of mixed units, geometrically speaking, and by mixed units I mean, notice this is 1 meter long and this is 52 centimeters wide. Just remember, when you set up ratios, the units must be the same if you're comparing apples with apples. In other words, if you're comparing, if you're comparing, I don't know, let's say in this case, distance to distance, right? The units must be the same. Now, sometimes you might have a ratio where we're considering comparing distance to time, and therefore you can't.
Or like miles per hour?
yeah, miles per hour would be a rate. And so therefore you can't convert miles to hours or vice versa. But when you have distance compared to distance, then absolutely we got to make sure that we have like units. All right, McKinley, what do you remember about metric conversions?
You have to either divide 1 meter or multiply 52.
Boy, that is 100% correct. However, most of us think about it a little bit easier. When we think about metric system, we think about one expression or one saying, phrase. Do you guys remember what the phrase is?
Oh yeah, like King Henry won't let me eat apples or something like that.
Yeah, well, something like that, right? You remember what it is now?
King Henry doesn't. I don't know.
It's something about chocolate milk.
Yeah, King Henry something something chocolate milk.
King
King Henry is the boy, the crimson metric.
How about King Henry died by drinking chocolate milk? All right. Or
It's a little
whatever
morbid.
else makes sense to you guys. All right. The one thing that most students who aren't familiar with this, they mess up the B. The B stands for your base units. It doesn't stand for any metric prefix. However, the base units are meters, liters, and grams, MLG. The K stands for? Somebody.
It's kilo, hectares, deci, base, deca, centimeters, and meters. Or no, is deca?
Yeah, that's the one we got to be careful with. K stands for kilo. It means 1,000, right? The abbreviation is K. H stands for hecto. That means 100. The abbreviation is H. And then we got these two Ds. They are alphabetical. So which one would come first?
So deca.
Deca comes first. It stands for 10. Decade, deca. That's another way of remembering it. It is the only one of these prefixes that has two letters, DA. B is your MLG, your meters, liters, and grams. The second D is 0.1, right? A tenth.
So deci.
Deci, except that in the English-speaking world, we want to say deci, but deci in Latin, sure. C is
Then centi and milli.
right? And centi means 100th. C and M stands for milli in Latin. That's 1,000. All right. King Henry died by drinking chocolate milk. How does that help us? Well, remember, to convert from one unit to the next, if we use imperial units, I don't know if you know how many inches are in a mile. Well, most people don't know that. However, for metric conversions, it makes our life very easy because you only need to remember one thing. King Henry died by drinking chocolate milk. So here are a couple examples here. I want to convert 3.5 meters to centimeters. Here's how it's done. Step number one, you take the first unit, meters. Meters would be not the M, that's milli. Meters would be the B. So that's our starting point, and I'm going from meters to centimeters. So I'm going 2 letters to the right. That coincides with how many decimal places you move it and the direction. That's what makes this as powerful. Once again, I'm going from meters, 1, 2, to centimeters. So I'm going to move the decimal place 2 places to the right. Originally, it was 3.5. If we move it 2 places to the right, we would get 350 centimeters. And that's the power of the metric system, is that you can do conversions very simply.
But what if I want to convert it beyond the M to?
Yes, so then we need a longer saying than King Henry died by drinking chocolate milk.
And then his wife.
Do you know the next letter?
No.
What is a 10,000th? What is a 100,000th? What is a millionth?
Metrica?
So I would assume a 10,000th would be a D, right? Because that would be like.
Well, we'll have to look it up. So I know a few of them. That we have. Let's see. We have a pico. We have a micro. We have. That's actually all I can name off.
Oh yeah, and then we have like macro up at the top, right?
I don't know.
King Henry drank bad chocolate milk,
Right.
and then he got a foot disease from eating too much.
All right. Well, luckily, these are the ones that we have to remember tonight. So if we want to convert deciliters, right? Deciliters, that's the D. Deci, deca, deci. So that's this one. All right, if I go from the deci to the hecto, right? If I go from deci to hecto, that would be 1, 2, 3 to the left. Therefore, I take 27. Now the decimal place is originally right here. And if I move it 1, 2, 3 to the left, we would get 0.027 deciliters or hectoliters. So that should be an HL, not a DL. How come I didn't catch that in period 1 or period 2? I don't know. All right, so that would be 0.027 hectoliters. All right, so that's how you do your basic conversion. Let's get back to our problem. Let's see, what was our problem? Oh, a couple more examples here. All right, kilometers to meters, kilometers to meters. Well, K is the only one, that's kilometers. And going to meters, you really want to go to this M, that's the milli. B is your meters. All right, so let's see why that is the answer. Well, we got to go 1, 2, 3 decimal places to the right. So if I write 4.3, that was my original number, and I go, I'm just putting a bunch of zeros here. If I go 1, 2, 3 to the right, we see that we get 4,300 meters. Okay. Same thing if we want to go 40 meters to or millimeters to meters. I'm going from the I'll do this one red. I'm going from the M for millimeters to the M for meters. So I'm going 1, 2, 3 to the left. So I take my original number 40. I got to go 3 decimal places. There's my decimal originally. I got to go 3 decimal places to the left. So 1, 2, 3. That's why it's 0.04. I can leave off this 0 right here. All right, that's how you do decimal conversions. King Henry died by drinking chocolate milk, and just follow the pattern of the letters. The other common mistake is that you count the letter that you start with. You do not count the letter you start with. So if we start on B and I'm going to M, I don't count the B as 1. I count 1, 2, 3. If I'm going from B to K, I don't count the B as 1. I go 1, 2, 3. Questions on that?
Nope.
Back to our ratios, this is our problem. We got a poster. I assume a poster is a rectangle. It says it's 1 meter long and 25 or 52 centimeters wide. I need to find the ratio of width to length. So I need width to length, but we got a choice. We can either change meters to centimeters or centimeters to meters. I'm going to do both just to show you what happens. If we decide to convert meters to centimeters, right? If I can decide to convert meters to centimeters, right? Well, I know that we have 52, I'm sorry, if I decide to convert centimeters to meters, so if I start with 52 centimeters and I want to convert to meters, well, let's see, once again, so we start with King Henry died by drinking chocolate milk. So if I go from centimeters to meters, I'm going from this letter to this letter, so I'm going 1, 2 to the left. So I've moved it 1, 2 to the left, I get 0.52 meters. So 0.52 meters would be converting centimeters to meters. Let's see, what is our ratio? We want to go width to length, width to length. So the width originally was 52 centimeters. We've now found that it's 0.52 meters. So that would be 0.52 over 1, because there's 1 meters, and that looks like the weirdest fraction I've ever seen.
Which then you would have to change to it if you would have done centimeters. So it's just giving you more work.
All right, it is giving me more work, right? So let's see, now, how could we turn this into a whole number? Well, we can always multiply the top and the bottom of a fraction by any number, as long as it's the same number. I'm going to choose to multiply this by 100, because that would move the decimal place. And if I do that to the top, I got to do that to the bottom. So if I multiply by 100, that would move it 2 places, and 1 times 100. Long story short, I would get 52 over 100. If I reduce this fraction, 52 over 100, I eventually get to 13/25. All right, just divide top and bottom by 4. What would have happened if instead of converting centimeters to meters, I went meters to centimeters, right? Well, let's see what happens. So if I want to do the other conversion, convert 1 meter into centimeters, well, let's see. If I want to go from meters to centimeters, meters is right here. Oops, I'm not drawing. If I want to convert meters to centimeters, I would go 1, 2 to the left, or to the right, sorry. So that would be 1, 2, that would be 100. So there's 100 centimeters in 1 meter. If I write that fraction now, right, W over L, 1 meter is the length, so I'd get 100 on the ball, I get literally the same fraction. So the point I'm trying to make here is it doesn't matter which one you convert, you will get exactly the same answer. Now, a thinking person would try to save themselves a little bit of trouble. Clearly, the second way was a little bit easier. So it is always easiest to convert the large unit to the small rather than the small to the large. Generally speaking, when you convert the small to the large, you wind up with a decimal number. That's generally speaking, not always true. If this had been 5,200 centimeters, converting it to meters, that would not have given me a decimal number. But it's generally easier to convert from large to small because you wind up with non-decimal numbers. Okay, so that was the kind of the review of what we've seen before. Now the rest is new. I mean, this is brand new stuff. The nice thing is it is pretty darn easy. So looks like we got, this is not geometry, this is more probability statistics, but let's see. We got a bag of marbles, and the only thing in the bag are red, blue, and green. And it says there are twice as many blue marbles as red marbles, and there's 4 times as many green marbles as there are red marbles, right? Once you're given this initial information, they're going to ask you to write some ratios. Here, I want you to write the ratio of red to blue, red to green, and blue to green. So McKinley, read this and tell me, what is the ratio of red to blue?
There are twice as many blue marbles compared to red marbles.
So what would be the ratio?
2 to 1.
And which gets the 2 and which gets the 1?
Blue gets the 2 and red gets the 1.
I agree.
Yes, I did it. Yes.
All right, Allie, do red to green.
So it'd be 1 to 4.
Okay. And Jack, do blue to green. Wait, it doesn't go blue to green. Or does it? Ah! I hit the darn mouse button.
Well, blue to green would probably be 2 to 4, which would also be 1 to 2.
Oh, notice they don't anywhere in the text tell us blue to green, but I do know it because it's sitting right here. So I can get blue to green just by looking at what we're given. It says if you have, and we don't know how many total marbles there are. This is just the ratio. We know that for every red, there's 1 blue one. So we can consider reduced form, there's at least 2 blue marbles, right? We don't know how many blue to green there are, but we know that there are 1 red for every 4 green. So we know that at least there are 4 green. Therefore, whatever the ratio blue to green is, it must reduce to 2 to 4. So that's how you get that bit of information when you are not giving it. Even though I guess technically you can figure out how many you have based upon the other 2 ratios. Everybody get that? Okay, now we actually have seen that before. That was in pre-algebra. What we haven't seen before is the following. I got 3 colors. I can write a triple ratio. Right?
You can say 1 to 2 to 4.
I could say 1 to 2 to 4. We've never seen a triple ratio. Why haven't we seen a triple ratio? Because how would you write this in fraction form, right? And this one wouldn't have a fraction form. However, it does have a colon form, 1 to 2 to 4. So today, because we're going to be dealing with polygons, triangles, quadrilaterals, pentagons, hexagons, we're going to be dealing with ratios in colon form that have more than 2 numbers. We might see something that goes 4 to 8 to 6 to 2 or something like that. And we will see those types of ratios. So this isn't necessarily a huge leap of faith, but it certainly is new. You've never seen a triple ratio before. All right, so what would this look like in geometry, which is what this is all about? This is what it would look like. In French, they call it the pièce de résistance. Have you ever heard that before, or that expression?
Yeah, I've heard that before.
What does it mean?
It means the piece that's resistant.
That is the literal translation in French. It means the piece of resistance. But what does it mean in common usage? Like, why do I use the word pièce de résistance?
Because it goes against the norm, I guess? Like, it's better?
It has that flavor a little bit.
Extraordinary.
But if you could
Yeah.
imagine a whole bunch of ice cream with whipped cream, and on the top of it is a
Cherry.
the cherry on top is called the pièce de résistance. It's the thing that stands out from the other things, or the thing that makes it very unique, right? So now we're going to go on the pièce de, this is not a math thing, but I just wanted to throw that in there. So this is the pièce de résistance of today. The thing that stands out is this, and it will be easy. All right. So it says this. It says the measure of 3 angles of the triangle are in the ratio 2 to 5. Notice it doesn't say what any of the angle measurements are. It just says that they are in a ratio of 2 to 5. And then it says somehow we're going to use this information and figure out exactly what's the angle measurement of the 3 angles. It seems like this isn't possible because nowhere in here does it say what any angle is in angle measurement. It just has a ratio. The ratio has nothing to do with the angle measurements. That doesn't mean it's 2 degrees, 2 degrees, 5 degrees. It means the ratio of the numbers are 2 to 5. So the question is, well, how do we do this? Right? We
have an isosceles triangle.
We clearly have an isosceles triangle. I know that because 2 of the ratio numbers are exactly the same. If this was 2 to 2 to 2, it'd be easy. It's equilateral. There'd be 60 degrees. But once again, just because we know it's an isosceles triangle, I don't know how big the angles are. I can at least surmise this. I probably can surmise that is this an
obtuse triangle
or an acute triangle?
This is an obtuse triangle.
This is definitely an obtuse triangle. But once again, it doesn't tell me what the angle measurements are. Here's how this, and this is pretty slick how this works. So here's how it works. We will let x represent the unknown number that when you multiply 2 by, you get to the angle measurement, right? Further, we will use the fact that we know, since it's a triangle and it's on a plane, that the angle 1 plus angle 2 plus angle 3 is 180 degrees. Now watch how slick this is. I know this is the ratio. If I simply just attach x to these 3 values right here, 2, 2, and 5, then that's what has to add up to 180 degrees. If x represents the number that I would multiply 2 by to get to that angle measurement, then it would be 2x plus 5x equals 180. This will work for any ratio if you're told something about the value of the things that you're comparing is. So for instance, if we were talking about the ratio of apples to oranges, and I said something that's in a ratio of 2 to 5, there's 2 oranges for every 5 apples, and I said that there are a total of, 20 total fruit, right? We could absolutely solve it that way. 2x plus 5x equals 20, right? That one didn't work out because of the math. How about 2 to 8? That would work out. So 2x plus 8x equals 20, then we can figure this out. All right.
But wouldn't that not be a real triangle because 2 plus 2 doesn't equal more than 5?
Well, once again, this is, I hear what you're saying, but remember, we're talking about angle measurements, not side measurements.
But those are the, oh, okay.
All right, I had to think about that one for a second. All right, 2x plus 5x is?
9x.
Therefore, x is equal to?
20.
Now, that's not 20 degrees. That's just the multiple that we will use with these ratios right here. To find out what each angle equals, we start off with the ratio and we do the multiplication. So this one is going to be
40
degrees.
And then the other one's going to be 40 because
40. Therefore,
and then we have
100.
And
100.
It's an isosceles obtuse triangle. That's pretty darn slick how that works. So you'll be given a ratio. You'll be told the shape it is. You're going to have to know something about what they're talking about. For instance, they could also frame this in terms of side measurements. They could say that all the sides of the triangle, right, would be 2 to 5. Now, Jack was right on this one. We couldn't.
But then you'd have to get a
it would have to be something like 2 to 6 to 5 or something like that.
Well, it would just have to also. You would also have to have a number that they all add up to because they don't add up to 180.
Right. So they would have to give you the perimeter. instead of angle measurements. So they're talking about sides, they would have to talk about like perimeter. And it would work the same way. All right, one more time. Let's see, once again, we're dealing with triangle and we're dealing with angles. And this time the ratio is 5 to 7 to 8. Okay, it's done exactly the same way. You let X represent a measurement of an angle, right? So therefore the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is 180. We simply attach X to each one of these numbers in the ratio and just solve that equation. 5 plus 7 is 12, plus 8 is 20. Therefore, X equals?
9.
9.
Okay, so therefore, what are the angle measurements?
So then we have 5. So we have 45, and then we have
63
and then we
and
have
72.
There you go.
Wait, I have a question.
Yes.
So can we just add the numbers up and then divide that by 180?
Well, yeah, I mean, that's literally what we're doing, sure.
Yeah.
All right. Any questions? So that was the pièce de resistance. I'll just show you. They'll start off with homework. We'll ask you simply to reduce a ratio. That's not big of a deal. That's absolutely what the algebra review was on. But then they'll give you some geometric shape right here and ask you to create a ratio. So for instance, let's see a hard one. Number 10, McKinley, do number 10 here. What's the ratio of IT to DT?
IT is 1. No, IT is 2, 1, 2.
I'm still with
Yes. No.
IT?
Very quiet.
Because you were
IT.
breaking up.
Oh, IT is bigger than DI, so that means 12 plus 4 to 10, or 2.
bigger than DI, but is it bigger than DT? Is the question.
IT is not 12. IT is
4 plus 12.
which would be
A number. I don't know. 16.
16 over or colon, either one.
10.
Where are you getting 10 from?
DI is 10.
This has DT.
Oh, sorry. DT is 22, 26.
There you go. So there is number. Now you could reduce that and they will. All right, that's this one. How about number 16? Says the ratio of the lengths of two segments is 4 to 3 when they are measured in centimeters. What is their ratio when they're measured in inches? Ugh.
It's 4 to 3, always.
Yeah,
What is it?
it's 2
Yeah.
to 1.
It's always 4 to 3.
It's always 4 to 3. That's what I was showing you before. It doesn't matter what the conversion is. If the conversion is 4 to 3 in inches or centimeters, it's going to be the same thing in the other measurements. So that one is, I don't know if you want to call it a trick question, but it's trying to get you to realize that the ratio doesn't change based upon what units you are using. Okay? All right. And then let's see. We'll just do 17 and call it a break. So let's do 17. So it says 3 numbers aren't known, but their ratios are 1 to 2 to 5. So I don't know what the numbers are. I don't even know what the shape is, but I know that they are in the ratio of 1 to 2 to 5. Is it possible that the numbers are 1, 2, and 5? Yes or no?
Yes.
Absolutely, because remember how you do this, right, is you would set it up as 1x plus 2x plus 5x. If x is the value 1, then you would get 1, 2, and 5. Could it be 10, 20, and 50?
Yeah.
Because then the x is equal to 10. Could it be 3, 6, and 20?
No. It would
Well,
be 3, 6, and 15.
Double would be 3, 6, and times 5 would be 15. And lastly, could it be x, 2x, and 5x? And obviously the answer is
Yes, it could.
It could be. All right. Cool. Yeah, that's it. That's it. Questions? All right, we have now reached Thanksgiving break. Seems like we've only started a couple weeks ago, but it was actually 3 months ago that we started in August. And we're 3.5 months ago, and we're already here. So I graded all the tests. Let's see. Ben got a perfect paper, and the rest of you didn't.
I did?
What?
Yeah.
What did I miss?
Look on your comments under.
did?
See it. Right.
I
And
didn't even know I got
Ben was, let's see, Ben got the proof right, Jack got the proof right, and I think they were the only ones. I don't think anyone else, if I remember right. I want to say Allie came close. She just had one thing, and I could be wrong about Jack. Oh, actually, Jack almost got the proof right. He missed one step. His logic.
I left out reflexive. You're cutting me off for leaving out reflexive.
Sorry, I've been saying that from the start, right?
I think this is the first proof that Jack and I have both missed on a test.
Right.
It's the first proof I've missed.
Well,
Me too.
to me, when someone misses it, that means that they just had faulty logic. If you have faulty logic, you absolutely miss the proof. But if your logic was good and you left off a step, okay, granted, you're going to lose a point or two. But, I mean, the important thing is to understand the logic. All right. I don't have anything else for you guys. You guys have a wonderful Thanksgiving break. Go ahead.
Funny story. I missed the first half of class because I was working on a different assignment, and I looked over my laptop and I'm like, oh, the Zoom is running. So
luckily you caught the last part, which is the most important part.
Yeah, so
I will post the class though. I mean, recorded the whole thing, so I'll post it within about 10
I also need the answers to the homework, so that's something.
Okay, gotcha. All right, cool. I'll have it up in 10 minutes.
Okay, thank you.
All right, you guys have a wonderful Thanksgiving break, and I will see you guys in the flesh on that Monday.
Goodbye. Have a nice day.
Later.